In this section we're going to talk about dynamic routing, and let's start with the dynamic routing protocols. Static routing allows routing tables in specific routers to be set up by the network administrator. Dynamic routing uses routing protocols that dynamically discover network destinations and how to get them. Dynamic routing allows routing tables in routers to change if a router on the route goes down or if a network is added. In dynamic routing, routing protocols running in routers continuously exchange network status updates between each other as broadcast or multicast. With the help of routing update message sent by the routing protocols, routers can continuously update the routing table whenever a network topology change happens. And let's go. Here is figure versus guys, static routing versus the dynamic routing. Static routing is a manually configured routing entry and must be manually updated if topology changes. This is suitable for very small networks and requires less CPU usage, and that may be fine to use to or from a stub network. Static routing we can use in a stub network, and it is easy to implement. We're just writing one statement that points a destination and the subnet mask and the next hop. Let's go ahead with the dynamic routing. Dynamic routing uses routing protocols that dynamically discover network destinations, as you know, and automatically update it if topology changes. That's the biggest advantage, one of the biggest advantage when you compare with the static routing. And that is suitable for large networks because of this. And we have rapid convergence times for the dynamic routing, and we may require more CPU. Let's go ahead with how dynamic protocols work. Router sends and receives routing messages on its interfaces firstly. Then router shares message with other routers using the same protocol. In the third step, routers exchange router information each other. And lastly, if router detects a topology change, it advertises this to other routers. Let's go ahead with IGPs and the EGPs. Actually guys, we have two types of dynamic routing protocols, and they are IGPs and the EGPs. IGPs are used to exchange routes in the same autonomous systems and support small, medium and the large scale organizations, but scalability is limited. For example, this is the AS number 100, and as you see, and here is the inside of the AS100. So in here, the protocols I'm using are the IGPs. Alright, let's go ahead. And IGPs can quickly converge to network, and the most commonly used IGPs are EIGRP, OSPF, and the use of RIP is very limited, and ISPs also ISIS as the IGP. And let's go ahead with the EGP. EGPs are used to exchange routes between different autonomous systems, and BGP is the only EGP used today. The main function of the BGP is to exchange a large number of routes between different autonomous systems. For example, here is AS200 and here is AS100. If you want to exchange routes between AS100 and the AS200, we're using EGPs, and the BGP is the only EGP we are using today. Let's go ahead with the dynamic routing protocol classes. We have three classes of the dynamic routing protocols, and they are distance vector, link state, and the path vector. Distance vector protocols routes according to the hop count, guys. Every router knows as much as its neighbor tells him. There is no network map on the routers. For example, RIP and EIGRP are the distance vector protocols. Let's go ahead with the link state routing protocols. Routers running the link state routing protocols can extract the topology map of the entire network. That is, they have knowledge of all the ways between 2 points. Thus, they collect all the subnets in a tree and make the best decision about which way to go with the shortest path algorithm. They decide according to bandwidth, delay, and something like that. And the link state protocols are OSPF and the ISIS. And let's go ahead with the path vector routing protocols. Route information is used to determine the best routes. Similar to distance vectors, routers do not have a network map in path vector routing too, and the BGP is the only path vector routing protocol. And here is the versus between distance vectors and the link state protocols. Distance vector protocols require that a router inform its neighbors of topology chains periodically, and they are RIP and EIGRP, as I told you in our previous slide. Link state protocols have the complete map of the network topology, and they choose the best path relying on their topology table, and we have no neighbor dependency in here, and OSPF and ISIS are the link state protocols. And let's go ahead with the classful versus classless protocols. Classful protocols, in classful protocols, subnet mask is not sent in routing updates, and we can use class A, B, or C routing. We can make class A, B, or C routing by using the classful protocols. And as they are classless, as they are classful, we have no CDR or VLSM support, and RIP version 1 and the IGRP, which is the old form, the EIGRP, are the classful protocols. In classless protocols, subnet mask is sent in routing updates, and we can make classless routing, so we have CDR and VLSM support, and RIP version 2, EIGRP, ISIS, and the OSPF are the classless protocols. Here is a general routing protocols comparison chart, and here are the distance vector protocols, RIP and EIGRP. BGP is path vector, but you may also see it as distance vectors in somewhere. The link state protocols are ISIS and the OSPF, as you can see. The classless ones are the RIP version 2, EIGRP, ISIS, OSPF, and the BGP. And if we want to check the VLSM support, as I told you in our previous slide, we don't have VLSM support for RIP version 1. We can use the RIP in small size networks. We can use EIGRP, ISIS in the large networks, and we can use BGP in very large networks as internet as well. And the metric count of the RIP is the hop. EIGRP has the composite metric. ISIS has the metric. OSPF's metric is known as cost. And BGP has path attributes as the metric. And we are gonna take deeper look to all of these features on our later sections. And if you want to check about the convergence time, RIP can converge slow, EIGRP can converge very fast, ISIS and OSPF fast, and BGP is the slowest converging protocol. Let's go ahead with the distance vector, dynamic routing, and RIP and the RIPng. Alright guys, when routers use the distance vector protocols, they send updates to their neighbor so they only know what their neighbor says and they don't know the whole details in the topology. RIP and EIGRP are the most commonly used distance vector protocols. As I told you on our previous slide, RIP is a distance vector protocol. Routers that are using RIP protocol create their routing table based on information exchanged between routers, and these routers send routing updates each 30 seconds to each other as broadcast for RIP version 1 and as multicast in RIP version 2. RIP uses the Bellman-Ford algorithm, guys, and the actual metric of RIP is the hop count. RIP can support a maximum hop count of 15 routers. For example, as you can see on the screen, if you want to reach from the router 1 to 10.0.0 network, 10.0.0.0 network, the best path will be the path above, because we use just one more hops to get the destination, but for the link below, as you can see in here, we use 2 more hops, which means 2 more routers to get the destination, and which means a worst path for the RIP. That's why we are using this path instead of this path if we are using RIP as a dynamic routing protocol. So let's go ahead with how we can establish a routing table in RIP. In the first stage, all routers install their directly connected networks to the routing table. As you can see, router 1 installs 1041 and 1042. This guy installs the 42 and 3, and this guy installs the 43 and the 44. Then in the next stage, routes are exchanged between neighbors and the routing tables begin to grow. As you can see in here, this guy knows this networks firstly, and router 2 knows about this, and this guy knows about this one. Then they are starting to exchange routes with each other. For example, router 2 says router 1 that, hey router 1, I have a network which is 1043 and that is directly connected to me, which means 0 as hop counts, and router 1 installs this to its routing table. As you can see, the network 104300, and the interface is the fast Ethernet 00, as you can see, and the hop count is 1, because router 2 is saying that, hey, 1043 is directly connected to me. Router 1 gets this update and says that, router 2, if this guy is directly connected to me, if this guy is directly connected to you, I'm sorry, it means 104300 is 1 hop away from me, which is actually you. Okay, then after all routes are exchanged, and as you can see, full routing table is established. For example, router 3 announced this route 44 route to router 2 and told that this guy is directly connected to me, and router 2 installed this as the one hop away and advertise this route again to router 1. Router received it and told that, hey, router 2, if this route 44 is one hop away from you, that means it is 2 hops away from me, and installed it with a hop count of 2. And here is the configuration of the RIP. That's pretty straightforward, guys, and let's go ahead. In router 1, router 2 and router 3, we are configuring RIP in this example. We are typing in the config mode router RIP, as you can see in here. And if we are gonna use the RIP version 2, we are typing the version and the 2, version 2. Then, what you're gonna see in here is, for router 1, we have 2 directly connected networks, and we are writing these guys in classful state. As you know that this is a B class network, this is an A class network, so I'm typing the network statements as the classful states. For example, network 10.0.0.0 for this network, and I'm typing 172.16.0.0 for this network on router 1. And for router 2, the same logic. It's just connected to the 10 networks, as you can see, this guy and this guy. So that's enough that I just type network 10.0.0.0 for this. And for router 3, I'm typing the 10.0.0.0 and the C class of this network. Alright, that's pretty cool. And to verify the RIP configuration, we can use show IP protocols command, and we can display the routing protocol we are using, which is RIP in here, and we can see also the update timers and the invalid and flush and the hold on timers as well. And to verify the RIP configuration, we can also use the show IP routes command, and in the routing table, as you can see, we have some entries by the R keyword, which means the RIP. Okay, and if we were to check the router 2's IP routing table by using the show IP route command, we can see the R commands, R keywords in here as well, which is RIP. And for router 2, that's learning this network and this network from this guys. As you can see, I'm learning the 16.0.0 network via 10.42.0.1, which is here, and I'm learning the other network via 10.43.0.3, which is here. Let's go ahead with the RIPng. RIPng, RIP Next Generation, is an extension of RIP for supporting IP version 6. The maximum hop count, again, we can use in RIPng is 15. So let's go ahead how we can configure the RIPng in here. To configure the RIPng, the first thing we should do on our routers are enabling the IP version 6 routing by typing IP version 6 unicast routing for each router. Then we are getting into the interface modes. Here is the difference from the RIP configuration. In RIPng, while we are using RIP Next Generation for IP version 6, we are configuring the IP version 6 statements under the interface modes, as you can see in here. So we are getting into the interface mode by typing for router 1, for example, interface geek 00, and the command is pretty straightforward. IP version 6 RIP a keyword which we can use arbitrary. This is myrip for this, and we are typing enable. Okay, that's pretty straightforward, and the same thing for the other interfaces as well. And to verify the RIPng configuration, again we can use the show IP version 6 protocols this time, and we can see that the IP version 6 routing protocol and the routing protocol name, as you can see in here, which we configured as myrip for the previous example. And we can also use the show IP version 6 route command, and we can display our full routing table, and we can see the routes learned by RIP again in here. Let's go ahead with the link state protocol. Routers that are using the link state routing protocols have the complete map of network topology, and they choose the best path relying on the topology table. In link state routing, we don't have any dependency to our neighbors. We don't care about what they tell us as the distance vectors. OSPF and the ISIS are the most commonly used link state algorithms. Let's go ahead with the DJIKSTRA algorithm. We have algorithms that we use for link state routing, and one of the most popular is the DJIKSTRA. DJIKSTRA is an algorithm for finding the shortest paths between nodes in a graph, which may represent, for example, row networks. OSPF and ISIS use this shortest path algorithm to determine the best path. In this algorithm, we have cost values for each path representing the bandwidth of the path, and lower cost means higher speed, guys. There's a reverse logic in here. For example, best path from A to E through A to C, C to D, and D to E, we have a cost of totally 10 in here, 1 plus 6 plus 2. Okay, we can also go from the path A to B and B to E as well. Oh, I'm sorry, this is actually not 10, this is 9. Okay, 1 plus 6 plus 2 is 9, and if we were to use this path, our cost is totally 10. And remember that if we were to use RIP in here, the metric would be the hop count, and this path this time would be preferred because we are using the just one more hops to get the E, while we are using 2 hops in here. Let's go ahead with the link state routing operation. We have 4 steps of the link state routing operation, and in the first step, routers discover their directly connected neighbors and send the hello packets. In the second, routers build link state packet LSP, which has the link state of directly connected links. In the third, LSPs are flooded to all neighbors and stored in a database. In the fourth, database is used for constructing a full map of the topology. Let's go ahead. As I told you in the first step, routers discover their directly connected neighbors and send hello packets and receive a hello reply back from each neighbor running the same protocol. In here, as you can see, the first step of the link state routing operation is sending and receiving the hellos, and here router 1 is sending the hellos from each interface and receiving back the hello packets from the router 2 and router 3. Secondly, routers build the link state packet, which is LSP, and which has the link state of directly connected links. For example, in router 1's LSP, we have the informations containing the Ethernet network, which is 1041.28.0, and with a cost value of 5, as you can see in here. And we have also this serial point-to-point link between router 1 and router 2, which is 1041.26 and 0 network, which has a cost of 10. And we also have the serial point-to-point link between router 1 and router 3, which is 1041.27.0 with a cost of 15. In the third step, LSPs are flooded to all our neighbors and stored in a database. And finally, each router establishes a link state database and calculates the best path for destination networks. Best path results are adding to our routing table. Let's go ahead with the routing table. What is routing table? The routing table stores information about IP networks and how they can be reached either directly or indirectly. Routing table is used to reach the best path for the destination network. As you can see in here, in IPv4 router routing table entries, we have some fields. In the first field, this field is identifying how the network was learned by the router. For example, if it is learned with EIGRP, if it's learned with RIP, if it's learned with a static routing or something like that. The second field identifies the destination network. And the third field identifies the administrative distance of the protocol that we're using. And here, this field identifies the metric to reach the remote network. And this field in here identifies the next hop. This field in here identifies the amount of elapsed time since the network was discovered. And the last field identifies the outgoing interface on the router to reach the destination network. As summary, to reach the 10.1.1.0 network, I'm using EIGRP with an administrative distance of 90, and this is my metric, and I'm reaching to this network via this IP address, and this is the outgoing interface of the router to reach the destination, and this is the time amount of elapsed time since the network was discovered. Let's go ahead with the routing table terms. Cisco's IP routing table is not a flat database, guys. The routing table is actually a hierarchical structure that is used to speed up the lookup process when locating routes and forwarding packets. Within this structure, the hierarchy includes several levels. Routes are discussed in terms of ultimate route, level 1 route, level 1 parent route, and the level 2 child route. An ultimate route is a routing table entry that contains either a next hop IP version address or an exit interface. Directly connected, dynamically learned, and local routes are the ultimate routes. As you can see in here, to identify a ultimate route, we should see an interface or exit point, however you define, and that's the thing we should see in ultimate routes. A level 1 route is a route with a subnet mask equal to or less than the classful mask of the network address. A level 1 parent route is a level 1 network route that is subnetted. A parent route can never be an ultimate route, and a level 2 child route is a route that is subnet of a classful network address.